For this lab, we're going to study centripetal acceleration. And in order to do this, we're going to compare forces from two methods. One method where we balance the force of a spring against force of gravity, one where we spin it and calculate that the centripetal acceleration is caused by the spring. Then we're going to calculate the spring constant, which is just how stiff the spring is. So let's talk a little bit about the force that the spring's exerting. And this force is given by Hooke's law, which is force of the spring equals negative kx, where this is stretch of spring from its equilibrium point, so from where it started. Then we have k, which is the spring constant. This is just how stiff the spring is. And then you'll notice this negative sign right here. And all that the negative means is that if you pull to the right, the spring pulls to the left. The second thing that we need to know is we are going to spin a mass. Blue didn't show up real. So we're going to spin a mass. It's going to go around here. It has some velocity tangential just around the outside. And if you'll notice, as it goes around, if there wasn't anything pulling it back to the center, it would just go off in a straight line. So there is a force pulling it to the center, and in this case, that force is from the spring. So in this lab, the sum of forces, and in this case, we're looking at the forces towards the center of the circle, equals m mass times the acceleration towards the center. So this force over here is caused by the spring, and this is m, and if you remember from class, this is v squared over r. So now we have to examine this v, and you know that v equals change in displacement over change in time. So let's examine how fast this goes. So if we look at this, delta x is distance around the circle. So that's going to be 2 pi r, and then times number of revolutions, over delta t, which is your time. Very important to note that this number of revolutions per time, you have your revolutions per minute. That's what that is, number of revolutions per minute. You need to convert this to revolutions per second. And this brings your total force provided by the spring, combining these two equations, to the mass spinning around, which in this case is just the bob, to, we're going to call this 2 pi r, and I'm going to write this as revolutions per second, this whole quantity squared, divided by r. And that r just comes from right here, where this square comes from right here. And in both cases, this r right here and this r right here are the radius of that circle. So the first way we're going to calculate force is by hanging masses until this little pointer right here matches the little rim of that UFO looking thing. I've got a better picture coming up here in a moment. So if we notice, there are two forces from our force diagram. We've got weight pulling down, the spring pulling up. It's not accelerating. So what you wind up with, force of the spring minus or plus, we'll say negative weight equals 0. For a grand prize of the force of the spring equals mg. So that's one way to find the force. Now in your lab report, when we use the gravitational force of gravity pulling down on this to balance it, we call this Fg. A couple notes on the apparatus. This scale is in 40ths of an inch, and that is a horrible unit, so we have to convert this. The second note I want to talk about has to deal with when you graph. Normally you measure your 0 position when this is set to 0, which means as you stretch it, your spring stretch, which is your x-axis, will be how far this knob is turned. And note that each turn is 1/40 of an inch. So your spring stretch will be this delta r, which is this right here. And you'll get some F0, which is when this is set at 0, how much force does it take to balance. When you're ready to find the force supplied by the spring from spinning it, hook it up to this. This is pretty much just a drill that spins around and it gives you the RPM on this readout. The important things are the speed up and speed down and the freeze display button, which we'll talk about. But make sure that this is tight. Otherwise this thing will spin, and if it flies out, we don't want that to happen. So if we're watching this, and let's go ahead and start. So we'll start this up. It is spinning. And one thing I want you to notice about this is that if you take your finger off the handle, or off this up switch, it will keep on moving. So you have to let it rest. So what you do, press the up arrow, then you press freeze display when this is balanced. And the balance point is right at the midpoint of the mushroom thing in the middle. So if we're watching this, spin, you see the pointer goes just up and right there. So this pointer is going to point right as it passes the balance point, you press freeze. It will continue to go up, at which point it will then be spinning too fast. So let's talk about what happens then. So you can see that the pointer is moving too fast because it's above the little dial. So we press speed down, and as it drops, press freeze right when it's balanced again. You will do this for 2 measurements on the way up and 2 measurements on the way down, for a total of 4 measurements. A couple of procedural notes when you're using this. The scribe mark is on the interior of the screw. This tells you which of these settings, 0 through 20 and 40ths of an inch, you have stretched the spring. The scribe mark should always point directly at the scale. Scribe mark always directly at the scale. Second, when you are spinning it, the mass of the silver bob is stamped on the bottom of the silver bob. So this is the mass you will use when spinning it. Scribe mark always points at the scale. So the final thing that I want you to note, you're going to repeat these, but you need to move the screw the specified amount in the lab handout. So in order to do this, you will turn this knob, 1 full turn is a 40th of an inch, and you will match it to however many 40ths of an inch. So when you make a graph of force of spring versus stretch, delta x, that's just this right here is delta x, you will get an offset line, which should look like that. Your line will be prettier because you'll use graphical analysis. And you'll notice that this little offset right here is the force to stretch the spring when it's set at this 0 mark. So data collection. Overall, you need the radius. This is from the center line to the middle of the mass. When you hang the mass, you just need mass of the hanger's mass, and the bob's mass, all 3. When you are spinning it, you get the number of rotations over that set time, and the only thing spinning in that case is just the bob. So that's the only mass that enters that equation. Okay. Error analysis. You will compare your 2 forces. Compare forces. Okay. So the way you look at this, you will get the force from gravity, or we'll just call this the hanging method, equals your force from spinning. Which means you are going to get plus or minus. On this side, this is just plus minus your hanging masses. And let's take a look a little more in depth about the spinning masses, because they have a little bit more error in them. So let's look at this formula and analyze it for errors. We're measuring multiple things. We're measuring the radius, and we're measuring this revolutions per second. You measured RPMs, you're converting to revolutions per second. So if you know when you multiply or divide, you add your percent uncertainties on these numbers. You add your percent uncertainties. So if we look, we have 2 R's here. We have 1 R down here. So it is 3 times your percent uncertainty of radius measurement plus, how many here? Well, you measured it twice, it's multiplying twice, so that is 2 times the percent of your revolutions per second error. and then that total is going to be whatever percent it happens to be. And that's how you get your uncertainty bound. Remember to convert it to a number, please. So the first thing we're going to do when we're graphing this is we're going to compare this to the equation of a line, because our results should look linear. So the equation of a line is y equals mx plus b. So here's our data, where this is your F sub 0, which is the force needed to stretch it at 0. So this is your force centripetal or force gravity from hanging the spring or spinning the spring, respectively. So you've got your spinning method, hanging method. You're going to have two graphs, and this down here would be your delta x, which is the stretch of the spring. Now we're going to compare our two slopes. So you have k from the hanging method, which has a plus or minus error bar, compared to k from the spinning method, which has plus or minus, and hopefully you'll have your average value, like if this is the range for kg, and this is the range for kc, hopefully in this little area where they overlap, tells you that that's where the actual spring constant will be. So if you have any other questions, please ask, and I will see you in lab.